SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to today's lecture 7 on the series of modeling of multiphysics system. So from the last lecture we had moved to the segment of single physics analysis. So we are starting with individual domains of physical systems that includes heat transfer, mass transfer. That's what we will cover first. Then we will move on towards solid mechanics, fluid mechanics, and then some extent of electromagnetism and electrochemistry. So in this lecture, we will continue our discussions for the thermal transport and the thermal analysis. In the last class, we had seen what are the different modes of heat transfer. Since this is a multidisciplinary course, not just limited to engineering students, but can be also extended to applied science students in other divisions. We are going into some introduction, some UG level analysis for the different mechanisms, and then we will immediately jump into a more system level modeling. So in the last lecture we had talked about the different modes of heat transfer, what are the different resistances. These have something we have studied in the undergraduate programs. Then we moved on towards seeing how the heat diffusion equation is derived. It's a conservation of energy equation. You have an arbitrary volume and a system which is surrounded by a bound surface. The bound surface does not have to be continuous in nature, and from the bound surface the heat is being either released or being absorbed. So the change in temperature within this arbitrary volume is a function of the spatial coordinate, that is how the heat is diffusing, and also of the time, that is your temporal coordinate. So based on that we came up with an equation that was our Fourier's law, or the Fourier's second law of thermal diffusion. It was a parabolic expression. We had a time derivative del t by del t, and we had a second order spatial derivative del square t by del x square, y square, z square, and so on. We also saw that under different coordinate systems, the Laplacian would change, and accordingly we can take different extents of symmetry. If it is cylindrical, then we can ignore the theta dimension, we can take only r and z dependence. If it is spherical, we can ignore the theta and phi dependence, and we can only have a radial symmetry. So based on these, we were able to set up our heat diffusion. We also looked at different boundary conditions. Those were our Neumann type, Dirichlet type, and Robin type. So we finally moved into our analytical approach for the 1D heat diffusion. Alright, so let's again start this problem since we had left it up to a certain extent. So we had a one-dimensional body. So this is our 1D body. Now in this 1D body, we have our heat diffusion equation is rho Cp del theta by del t equals to k del square theta by del x square. How does this equation come up? You can rewrite this expression as rho Cp del t by del t is equals to k del square t by del x square, and we have normalized the t with respect to our initial condition and boundary condition in such a way that our theta is equals to some t minus some value t, let's say t infinity or t wall, t final over t some t star minus t final. It is in such a way that our theta at all x at time 0 is equals to theta naught, where our temperature at all x at time 0 is equals to T naught, and our theta for the boundaries at 0 and L is at a given time t. So x is equals to 0 and L is equals to 0, which means that our temperature at x is equals to 0 comma L at a given time t is equals to Tf. Okay, so our wall temperature is Tf, and we have our initial condition as T naught. Accordingly, our equation comes down to our initial conditions as theta naught, and our wall conditions x is equals to 0 comma L as 0. Okay. Then what we did is that we are using the separation of variables process. In the separation of variables process, we take the original variable, which is a function of both x and t, that is theta is a function of x and t, and we split it into two variables. A capital X is a function of x only or dependent on x only, and capital T is dependent on small t only. Right. This T is temperature, this T is a different variable. Please do not mix up with the two T's. Now, if we substitute this back into our equation, then we have 1 by alpha. The partial derivative of theta with respect to time is dt by dt into x, because x is only dependent on the position. And the second order partial derivative of our theta with respect to position will be d square x by dx square, and the t will come out because it is only dependent on the temporal coordinate. Now, we can see that we have replaced our partials with full derivatives, because x is a function of the spatial coordinate only and t is a function of the temporal coordinate only. Now, we have rearranged the terms. So, rearranging them, what we did, we took the t to the left hand side where all the t terms are, and the x to the right hand side where all the x terms are. We had 1 by alpha t dt by dt is equals to 1 by x d square x by dx square. This we are taking equals to a constant, and this constant we are taking as lambda square. Okay. There is a reason for taking it lambda square, and there is also a reason for taking it negative. Alright, so we will explain that. Okay, let us rewrite our expression one more time. So, 1 by alpha t dt by dt is equals to 1 by x d square x by dx square to minus lambda square. So, this is our expression. Now, we get two equations out of it. So, two ODEs out of this expression. What are the two ODEs that you can get? One is in terms of t variable a function, and one in terms of x. Okay. So, dt by dt is equals to minus lambda square 1 over t is equals to minus lambda square into alpha. And the second, that is equation 1, and the second one will be d square x by dx square plus lambda square x is equals to 0. This is our second equation. So, we have equation 1 and equation 2. These two equations can be solved independently. So, let us solve for 1. So, first order derivative with 1 by t. So, we will have t is equals to some constant a exponential of minus lambda square alpha into time t. Okay. This equation we can solve again in terms of x. X will be equals to some b cos of lambda x plus c sine of lambda x. Solving an ODE, these are very simple ODEs, first order or second order. These you very well know how to solve these. 1 by t dt by dt is typically exponential functions. D square x by dx square plus lambda square x, you can solve it for just like any ODE, second order ODE, you can find the solution. This is cos and sine lambda. Okay. We will put our boundary conditions first. Since boundary conditions are same for all time steps, it just depends upon x. So, we will use the x variable for this case. So, boundary conditions, let us rewrite them. Theta of 0 comma t equals to theta of some L comma t was equals to 0. So, x of 0 is equals to what is equals to 0 is b, and the c part is gone. So, the b comes out to be 0. Then that is our first boundary condition. Now, second boundary condition, x of L is 0 is equals to c sine lambda into L. Okay. For this equation to hold, that c lambda L equals to 0 to be applicable, either c has to be 0. So, one case could be that c is equals to 0. This is called a trivial solution. In this case, the entire equation becomes 0. We do not want that, right? So trivial solution. The second case could be that sine of lambda L is equals to 0. Now, what case does sine of x is 0? It is in the case of n pi, right? For 0, pi, 2 pi, 3 pi, for every case, for if you observe the sine curve, it will go to 0, right? So, lambda L is equals to n pi. In this case, since there is n, where n belongs to 1, 2, 3 and all the other numbers, even 0. So, lambda n L. So, we can put an n in this case because for different values of lambda, and then lambda n is therefore is equals to n pi over L. Okay. These are the eigenvalues of the equation sine of lambda L equals to 0. So, for the sine of lambda L equals 0, lambda n is n pi over L. All right. Now, we are coming to a position where we can start gathering our expression. So, lambda n is n pi over L. All right. X of x was equals to summation n is equals to 1 to infinity Cn of sine of n pi by L into x. So, what we did is now we have these n number of solutions of these are the eigenvalues of our given expression. We are adding them over, so that is a superposition. That is why we are taking summation. Now, since we are adding all the sine n pi L over x, the constants might also be different, right? So, we will have Cn where n is the integration constant, and those will be added up. All right. Our t of t is equals to a exponential. It was minus lambda square alpha into t. So, lambda is n square pi square over s lambda square into alpha into t. So, our theta was x comma t will be equals to x of x into t of t. So, which will be summation n equals to 1 to infinity. We can have our a exponential minus n square pi square by L square alpha t into c of n sine n pi by L into x. Okay. It's a little bit difficult to write this n pi by L every time, just let us take it lambda n for now. We can combine these two integration constants. So, we can combine them. So, we will have our theta is equals to summation n equals to 1 to infinity some a of n, just a into c of n, let us write a of n into exponential of minus lambda n square alpha t into sine lambda n into x. Okay. Now, we are down to one integration constant. This integration constant we need to get rid of, and here we will use our initial condition. So, our initial condition was that at theta at all x at time 0 was equals to theta naught. Now, if we want to put time 0 into this expression, we can substitute this theta at x comma 0 will be equals to summation n equals to 1 to infinity a n. This exponential term will be exponential of 0 is 1. So, this will become 1, and then we have sine of lambda n into x, and this is equals to theta naught. Now, how do we solve this? We have a n into sine lambda n x equals to theta naught. It looks like a Fourier series to me, right? So, we can do a Fourier series transformation and get a n in terms of theta naught. Okay. So, let us try to do that. So, we are doing a Fourier transformation, and a n will be equals to 2 over L integration 0 to L, that is our domain thickness, theta naught into sine lambda n into x dx. Okay. So, this is our Fourier transform. We took everything to the right, our domain was from 0 to L, that is why we integrated from 0 to L into 2 by L. Okay. So, let us integrate this out. So, our a n therefore is equals to 2 over L into theta naught. Okay, let us go back one step. We are solving for this expression, theta naught is a constant, it will come out of the integration. Sine lambda n into x, integrating is 1 by lambda n. So, 1 by lambda n cos of lambda n into x, there is a minus sign, and we will integrate this from 0 to L. So, let us write it a n is equals to 2 over L theta naught. Lambda n is L over n pi, in this case 1 over, and then we will have cos of 0 minus cos of n pi. Okay. So, this is our lambda n expression. L will get cancelled. So, we will have a n is equals to 2 theta naught by n pi. Cos of 0 is 1 cos of n pi. We can substitute this a n value back into our expression, but if you notice something, there is that if n is even, so 2 theta naught by n pi, n pi even means that cos of 2 pi is 1, cos of 4 pi is 1, this term becomes 0. So, this will be 0. If n is odd, in this case this will be minus 1. So, 1 minus minus 1 is 2. So, that will be 4 theta naught by n pi. Okay. So, this is our solution. We can therefore rewrite our theta of x comma t is summation n equals to 1 to infinity of our a n is 2 theta naught by n pi 1 minus cos n pi, and we have our sine of n pi by L into x, and our exponential of minus n square pi square alpha by L square into time t. Okay. Now, let us revisit our question, why did we select minus lambda square? So, this is our lambda term, n square pi square by L square. Had lambda been positive, then this exponential would have grown exponentially, right. So, your temperature profile, that is your theta, would reach infinity very quickly, right. Minus lambda square means that the heat energy is diffusing, or the heat energy is getting dissipated. That is the nature of this diffusion problem or a parabolic solution, that the energy or the system's momentum, when we doing momentum based equation, it needs to be dissipated, and the energy needs to be go out. So, in that case, if we take plus lambda square, then this exponential of lambda square alpha t would have been positive. In that case, the solution would not converge, and the solution would explode. That is one reason. And why we took lambda square instead of lambda is that otherwise when we do this x term, we will have a square root of lambda instead of a lambda square, and these terms would not have been cos and sine anymore. These would have been cos hyperbolic and sine hyperbolic. You make a note of these when we will do solid mechanics based problems, and we will see the solution for plates. We will move from membranes to plates. In the case of plates, we will have a fourth order derivative, and the analytical solution for a fourth order derivative will have both cos and sine, and will also have cos hyperbolic and sine hyperbolic. The nature of the two are very different, right. So, it will be very interesting to see how a diffusion equation likewise would vary, or how can we use a wave equation instead of a diffusion equation in such cases. All right. So, this is our complete solution for lambda. We can quickly plot it before we go to the non-dimensionalization segment. Is over here. If we have a theta over here and t over here, and say this is our 0 line, then our temperature profile, initially we started with some theta naught temperature. So, this is our theta naught, and then our temperature profile would gradually decay and will go all the way down. So, it is at time t is equals to 0, and this is time t is equals to t. So, our temperature is gradually decaying because the heat is allowed to escape from the walls and out to the surrounding. Now, when we actually solve this expression, or we like to put this expression up in a simulation or a plotting software, in that case we cannot take infinite number of terms, right? That is not possible. So, what do we do in that case? We would take only the first 2 or 3 terms. We can see that this exponential term will become very large very quickly. As the n increases. So, it is no point taking more than 2 to 3 terms. You will see the first term is fine, pi square alpha L square into t. Second term will be 4 pi square alpha over L square into t, and then 9 pi square and 16 pi square and so on. This is, remember, that is exponential of minus n square. Right. So, this negative exponential will decay very fast. and therefore we can ignore fourth and fifth order terms and higher order terms, and we can take just the first three terms in that regards. Okay, so this finally became our expression for our transient thermal diffusion. And in general, most parabolic systems are solved likewise. Okay, we'll go into non-dimensionalization. Again, let's take a system. Let's take a box. Okay, the temperature over here is Tx comma T. We have our domain x is equals to 0 and x is equals to L. We have an ambient as T infinity. This has a property, we have a thermal conductivity, we have density, we have specific heat. Let's consider a 1D system. The thermal diffusion equation, now you should be an expert of this by now, right? So, the thermal diffusion equation rho Cp del T by del T equals to K del square by del x square is our heat transfer equation. Okay. Now, I would like you to, before I get into it, I would like you to pause the video maybe and try out how to non-dimensionalize this. So, we have done non-dimensionalization in lecture 3. Take some variables for x. So, x is between 0 and L, time you can take as T naught. I will give you the boundary conditions, initial condition. So, T at x comma 0 is equals to T hot. We have minus K dt by dx dot with n cap at x is equals to 0 and L is equals to H T minus T infinity. So, we have convective loss from the surrounding is H from both sides. Okay. So, these are our initial and boundary conditions. Okay. Now, we can see that, so if you like to give it a try now, so you can pause now and try to normalize these and then substitute back, and then when we can let's see that if we can converge to the same system. So, this is a learning process that you try it out first and then work it out with me. Okay. So, normalizing this equation, that is our first step. So, we will normalize the temperature as theta bar T minus T infinity over Th minus T infinity. Normalize our position vector by length, and we will normalize our time vector with some constant T naught. We will come to what T naught actually is. Now, we will substitute these. If we substitute these back into our governing equation, we will have rho Cp Th minus T infinity divide by T naught del theta bar by del T bar is equals to K by L square. Okay. So, these terms will get cancelled out. We can take everything to the left. So, the highest order derivative is our second order derivative with the position. So, we will take every constant to the left hand side. We will have rho Cp L square by K into T naught is equals to smart square. Okay. Now, select T naught equals to rho Cp L square by K, or the L square over alpha. Okay. For those who know, alpha is the thermal diffusivity, it is K over rho Cp. We have talked about it in the earlier class. So, L square over rho is a time constant. This is called the diffusion time constant. Okay. In terms of units, L square will be meter square and alpha will be meter square per second. So, meter square over meter square per second will be seconds. Okay. All right. So, if substitute this T naught into this, our governing equation will become del theta bar by del T bar will be equals to del square theta bar by del x bar square, and our initial condition will be theta bar at x bar comma 0 was equals to T hot. So, T hot will be 1, and our boundary condition will be minus del theta bar, or let's write it carefully. So, minus k Th minus T infinity over L del theta bar by del x bar dot with the surface normal at x bar is 0 comma 1 will be equals to h T infinity to theta bar at x equals to 0 comma L and at a given time t. Okay. So, we can again, our highest order derivative is this d theta bar by dx bar. We take everything else to the right. We will have minus del theta bar by del x bar with the surface normal. X bar is 0 comma 1 will be equals to h L by k into theta bar x bar at 0 comma 1, this is 1, it is not L, at a given time t. Okay. Now, we had a rule with our dimension analysis is that either we select a variable which can absorb these. For example, we had selected this time constant t over here, which can absorb all the constants together and make that term 1, or if we do not have any such variable that is unknown, in that case we can club together all the material properties into one number. This number is an important number and it is called the Biot number. Okay. So, our Biot number goes to HL by K given by Bi. So, a boundary condition therefore will be del theta by del x bar for the surface normal, and why I am writing the surface normal again and again is that the gradient of theta is a vector and you need to take a dot product with the surface normal, right. So, it depends on whether it is on the left hand side or whether it is on the right hand side, which boundary we are applying is equals to Biot number into theta bar at x bar equals to 0 comma 1 and time t bar. Okay. So, these will become our initial condition and our boundary conditions. So, with these set of values, if we would need to know our Biot number, if we know our Biot number, we can then solve this set of equation and we will be able to come up with a solution of theta which we can renormalize back into our original equation. Okay. With that, we have an understanding that this is our basis of heat diffusion. We are doing diffusive based heat transfer, we have convection from the surface. So, the heat is being given out to the surrounding through convection. We will talk about convection in depth when we go into multiphysics based problems. So, the convection becomes a combination of heat transfer and fluid dynamics. Right now, we are doing single physics based analysis. So, one physics at a time. Okay. Now, lumped body analysis. So, let's look back to our governing equation. So, our normalized governing equation, thermal model, we had del theta bar by del t bar was equals to del square theta bar by del x bar square, and we had our boundary conditions and initial condition equals to 1, and we had del theta bar by del x bar, the surface normal at x bar equals to 0 comma 1 is equals to theta bar and all time t. Okay. Now, we had a Biot number term multiplied with this. So, what does this Biot number signify? It's an important parameter. It's a material constant, equivalent constant, which is a combination. So, a Biot number is a ratio of our conductive resistance to our convective resistance. So, the conductive resistance we have seen earlier when we were in the last lecture, the equivalent conductive resistance for a system was L over Ka and convective resistance 1 over Ha, where K is the thermal conductivity of the body, H is the convective heat transfer coefficient to the surrounding. Okay, so it is the heat being convected away to the surrounding. A will get cancelled, L is the effective length, so this will be equals to H L by K. Okay. Now, if we have this understanding that the Biot number, it is a ratio between the conductive pathway resistance versus the convective pathway resistance. So, a body which will have Biot number less than 1 will be either A, it will be very conductive, thermally conductive, or small in dimension. Okay. So a small body, a thin body, for example, if I compare this pen to this, and the effective length is this much, say this is around 2 centimeters and this is around 5 to 6 centimeters, right. So, in these cases, this will have a lower Biot number if these are of the same material, I am assuming. This body will have a lower Biot number compared to this body. That means that the heat can diffuse via conduction or dissipate via conduction very quickly in a thinner body compared to a thicker body. Okay, that is one. The second is if the Biot number is greater than 1, then A is that the body is poorly conductive, again thermally, or our dimension, the body is big, so big in dimension. Okay. Again, if you compare this pen to a metal rod of the same thickness, then this pen made up of some polycarbonate or some polymer will have a poorer thermal conductivity, so a larger Biot number, and heat will take some time for it to dissipate compared to a metal pen. Okay. Let us put this into, so the objective of this course is just not to go over this formulation, it is for you to realize and understand what each parameter means or behaves. So, you need to visualize. So, Biot number signifies the extent of conductive transport in a body, right, over convective losses. So, if I take any body, conductive transport means is that how well defined our temperature profile is in this body. So, if this is our temperature profile, T is a function of x comma T, how well defined is it? Is it flat? In this case, temperature is only a function of time, or is there a variation in the spatial coordinate, or that the heat can conduct out or can diffuse out, right. So, a Biot number, larger Biot number bodies are poorly conductive, which means that the heat from the center will need to face some resistance to dissipate out, right. So, the center might be at a different temperature compared to the surrounding. However, if a body is highly conductive, then the heat, whatever heat is being generated, can quickly go out from the body. So, in that case, there is no spatial variation, the temperature throughout the body is constant, there is only temporal variation, right. That is the significance of Biot number. So, for a Biot number less than 1, the conductive transport is spontaneous, or instantaneous, and no spatial variation. Okay, what this means is how do we get, so from mathematical perspective we understood, right? It is from physical understanding that a body is conductive, it is able to dissipate heat very quickly and the temperature is flat. That's a physical understanding. Mathematically, how do we get it? Again, if you look at del theta bar by del x bar was equals to Biot number into theta bar. Ignore for now the dot n and everything at a given surface. In this case, if Biot number tends to 0, what we get is this del theta bar by del x bar at the surface will also tend to 0, which means that theta bar at the surface will not be a function of x bar. So, there will be no spatial dependence, it will only be a temporal dependence. With this understanding, we need to revisit our energy balance. So, the last time our energy balance, it had whatever the heat was stored was equals to a negative of the heat being diffused out and then the heat being generated, right. So, that was the case. Now, in this case there is no spatial dependence, right. So, if we take the total heat in the word body, that is mCp del T by del T. In this case there is no spatial dependence, so we can replace the partial derivatives with complete derivatives, dt by dt will be equal to, how is the heat being going out? The heat is going out as convection. So, HA T minus T infinity. So, we have H and T infinity outside, our cross section area is A, our body's thickness is some L, our volume is V equals to A into L. With this or we can write this as rho into V into Cp dt by dt, so minus HA T minus T infinity. Okay. So, this becomes our governing equation, and our initial condition to solve this, T at time t is equals to 0 will be some temperature T naught. Okay, that will be our initial temperature. Perfect. Okay. What we can do is then we can try to solve this expression for our case, and we can say that dt by dt is equals to minus HA over rho CPV into T minus T infinity. Okay. Now, we are trying to solve this, we can normalize this expression. So, normalize, we can take theta bar as T minus T infinity over T naught minus T infinity, and our time as T over T naught. If we substitute this quickly into this, then T naught minus T infinity over T naught d theta bar by dt bar will be equals to minus HA over rho CPV T naught minus T infinity into theta bar. These gets cancelled, T naught comes to the right, we can select T naught is equals to rho CPV over HA. This is again our time constant for lumped analysis. We do get d theta bar by dt bar is equals to minus of theta bar. Okay. We want to solve this expression. So, if we solve this expression, we will have, so d theta bar by theta bar equals to minus dt. Time is from 0 to t. At time 0, our theta is 1. If you put this into this, we are at time 0, t is equals to t naught. So, t naught minus t infinity by t naught minus t infinity is 1. So, it is 1, and then we are going to theta. So, this will be natural log of theta. Natural log of 1 is 0, it's minus t, or theta is equals to exponential of minus t bar. So, all t bars, theta bar. Okay. We will come to electrical analogy in a second. Alright. Now, if we renormalize this expression, theta bar is t minus t infinity. So, we will have t minus t infinity over t naught minus t infinity is equals to exponential of minus t by t naught. What was t naught? Rho CPV over HA. So, it will be HA into t over rho Cp into V. So, this becomes our expression. For thermal variation in a lumped body. Okay. We can then find T based upon T naught and T infinity and our time constant, that is rho Cpv over HA. All right. Now we can have this relation to an electrical system. So, and consider an RC circuit where the capacitor is initially charged to some E naught voltage and discharged through a resistance R. Okay, so this is our circuit. So let's say that initially our switch was closed. We have a capacitor E naught. Okay, so this is our electrical analogy, is that our capacitor is initially fully charged and then we open this switch. As soon as we open this switch, our capacitor will discharge through this resistance and the voltage will gradually decay. If you write the voltage expression, our voltage expression is dE by dt equals to minus E over RC. Okay, this is our voltage expression at E at time 0 is equals to E naught. This is our initial condition. Okay, so if we solve this expression like last time, we will have E is equals to E naught exponential minus T over RC. All right, so our equation E is equals to E naught exponential minus T over RC, where RC is our time constant, is our electrical time constant, is equivalent to T minus T naught T infinity over T naught minus T infinity exponential of minus T rho Cpv over HA. Right. So, this is our thermal time constant. Okay. From this analogy, E naught is T naught minus T infinity or is comparable to T naught minus T infinity. Our time constant RC is comparable to rho Cpv over HA. Now, can anyone look at this expression and tell me what is the ratio of these two, or how does this time constant come? You could have some understanding from rho Cpv and HA, right? So, rho Cpv is our energy stored in the body, in the bulk, and HA is the energy dissipated out via convection. So, the ratio of the two gives us the time constant. Okay. So, this becomes our analogy. These are our time constants. This is our electrical counterpart. This is our thermal counterpart. What is the capacitive effect? In this case, the capacitive effect is that of the body. The body has some internal storage. So, say that it is myself, it is me, I am having some body temperature. Now, all of a sudden, say I die, and due to which my body is not able to generate or maintain the body temperature or the heat, and my body will gradually become cold, right. So, forensics, how do they determine what is the temperature of a body is through this lumped body. Our body is considered of uniform temperature, that it is, mostly it is of a uniform variation in temperature throughout. This temperature will gradually decay. Right now it is at 37 degrees Celsius, right, 98.6 degree Fahrenheit, and that temperature will gradually go down. So, we can find out the time if we know the different temperatures. Say we know that the final temperature at a given time, we can estimate the time from that case. If we know the time, we will be able to estimate when did that person die. Right. So, that is an example of forensic analysis where this lumped body or capacitive models can be used. Okay. Now, we are always assuming that this T infinity is a constant, right. So, mostly this T infinity term is a constant, and that is our ambient temperature. That is a well enough approximation. However, the T infinity may not be a constant, and the T infinity can have some variability. Say that it is in a water bath and the water's temperature is rising. In that case, we can say that T infinity is a function of temperature equals to Ti, some initial temperature, plus B into T. B is a constant, T is the time. Okay. So, if you want to solve this, we again look at our lumped body equation, our formulation, that rho Cpv dt by dt is minus Ha T minus T infinity. We take everything to the right and we write this in terms of some alpha star, right, so, some constant T. So, we have our expression as d by dt of T minus Ti. We are changing the variable. This is a change of variable basis, right. We are replacing T as T minus Ti is equals to minus T minus T infinity over alpha star. Alpha star is not thermal diffusivity, it is a combination of rho Cpv over Ha. Okay. So, this will be, if I replace T infinity over here, so T minus Ti minus B into T divided by alpha star. We can take this T minus Ti term to the left. So, we will have d by dt of T minus Ti, this is our variable, plus T minus Ti over alpha star is equals to Bt over alpha star. So, we have a homogeneous solution, we have a non-homogeneous solution, right, a particular solution. So, if that is the case, then we can solve the homogeneous equation. T minus Ti for the homogeneous part will be equals to some constant exponential of minus T over alpha star. Alpha star is our time constant. And for the particular integral, counterpart, T minus Ti for the particular integral will be equals to B T minus alpha star. Okay. So, our combined expression will be T minus Ti with the summation of these two will be A exponential of T over alpha star plus B T minus alpha star. This will be our solution for our expression. So, we have this exponential decay, but we also have this linearly increasing temperature for our bulk. Okay. Now, let us look at the numerical analysis of the diffusion problem. We are taking our old friend, our normalized equation, del theta by del t is del square theta by del x square. Let us take a q dot term as well, that is our generation term. Now, we have removed all constants, we have taken the time constant as L square by alpha, we have taken q dot normalized as q over k over rho Cp, and in those regards we have removed all the constants and stuff, k and q dot over k, and this is our normalized expression now. Okay. We are trying to solve this governing equation based upon three kinds of boundary conditions. So, our boundary conditions, our initial condition is the same, theta at all x comma time 0 is equals to say 1. Okay. Then our boundary conditions will be we can have 1 as our Dirichlet type, this will be theta at 0 comma t will be equals to some value say 0, theta at 1 comma t equals to some value say 0. This we have done in last class, I am just writing this up so that we can move to the numerical part. Newman part is d theta by dx at 0 comma t is equals to some flux q. Let us say for now heat is being input into the system or the heat is taking into the system, so minus 1, heat giving out is positive, minus d theta by dx 1 comma t is equals to 0. There is a reason I put plus in the case of d theta by dx at x is equals to 0 and a minus in the case of x is equals to 1 is because there are two boundaries. The normal component to the left boundary is in this direction and the normal component to the right boundary is in this direction. The gradient is always from x0 to x1. So in that case, our minus del theta by del x dot with the normal will be dot will be minus 1. So we will have multiplier minus 1, and that's why the minus sign gets removed, right. So we have minus del theta by del x, or rather minus of gradient of theta dot with the surface normal. This value at this end, the surface normal is towards the negative I cap, gradient will be towards the positive I cap. That's why you have an extra minus 1 term, and the 2 minus 1 cancel out to be equals to 1. This is our heat flux. The heat flux is negative. So negative heat flux indicates heat input, right. This is an adiabatic condition, that is that heat is not lost to the surrounding, right. And our third type of boundary condition will be our Robin based boundary condition. So Robin boundary condition will be mixed, right. So del theta by del x at 0 comma t is equals to some Biot number times theta. So Biot number, let us take is 1 times theta at 0 comma t, and minus del theta by del x at 1 comma t equals to, say, some Biot number. Let us take the first one as 1 and the second one is 0.5. Okay, minus plus, again this likewise the same thing. So these become our the governing equation. Now solving this expression, we can either do it explicit or implicit. We have done this in last class. Let us quickly go over the explicit part. So explicit is theta n plus 1 of I minus theta n of I by delta t will be equals to theta n of I plus 1 minus 2 theta n of I plus theta n of I minus 1 by delta x square. This is our unknown, these are our knowns, we take it to the left. Theta n plus 1 of I is equals to theta n of I plus delta t over delta x square of theta n of I plus 1 minus 2 theta n of I plus theta n of I minus 1. Okay, we need this value to be less than equals to 1 by 2. That is our stability condition for stability. So we select it accordingly. If you take delta x as 0.01, then delta t should be less than 1 by 2 of 0.01 whole square, and likewise. Okay. Now how to set this up? We have our initial condition that theta at all rows at time 0 is equals to 1. Now you can set up two for loops for j is equals to 220 and for I is equals to 2 to nx minus 1. We can put up this expression over here, theta ij is equals to theta ij minus 1 plus this dt over dx square, theta of I plus 1 for the j minus 1 minus 2 theta I j minus 1 plus theta I minus 1 j. This will be our expression. We will end this. Okay, and then we will put our boundary conditions. So the boundary condition part, let's write in the next step. So if it is Dirichlet, then theta of 1 for the jth time step will be equals to 0, theta of nx for the jth time step equals to 0. That is our Dirichlet. For the Neumann, we will have d theta by dx was equals to minus 1. So let us write that. So d theta by dx is theta 2 comma j minus theta 1 comma j over delta x equals to minus 1. So we can say theta, this is known, this is unknown. So theta 1 comma j will be equals to, if you multiply delta x over here and bring it to the left side, theta 2 comma j plus delta x, that is 1. And then for the other side, theta nx comma j will be equals to theta of nx minus 1 comma j. So on the left hand side. These are again for the Neumann type. And then for the Robin type, we had del theta by del x was equals to some theta bar. So this was theta of 2 minus theta of 1 by delta x equals to theta of 1. We can find out theta of 1 from here. as theta of 1 is equals to theta of 2 divided by 1 plus delta x, and likewise we can do del theta by del x for theta at x is equals to 0 and x is equals to 1. So, theta of nx minus plus theta of nx minus 1 by delta x is equals to theta of nx. So, we can find out these theta of nx from here, right. So, these methods we will finish, and then we will finish this with an end condition, right. So, our loop started from here, the second for loop after our set of boundary conditions, our Robin boundary condition will end. Okay, I am going slowly over these slides. These are done by an implicit scheme, and this is our solution. This is our initial time t is equals to 0, and as time progresses, now you can see that it is the same type of behavior that we have done analytically, t equals to increasing. So, this is for the Dirichlet case. This is for the Neumann case. We have a flux condition. In this case, I have taken flux as minus 0.1 rather than minus 1. And this is our Robin case. So, you can pause the video at each of these and you can look through this code for the analysis. So, with that we will end our discussion for today, and we will start with mass transfer in the next class. So, thank you so much for listening.